Today's lesson is going to be on science and steam engines. So we're going to look at using your knowledge of states of matter, that's solids, liquids and gases, to try and explain why a metal can implode. We're going to define combustion, complete some word and symbol equations. Go a little look at Sankey diagrams, do some research into steam engines, that's a task for you guys to do, and to explain why a steam engine could potentially explode. So something implodes, when it collapses inwards, in on itself. I want you to try and do it with a can if you've got a can at home, although you're not allowed to touch it, sit on it, chuck your brother or sister at it, chuck anything at it, smack it with anything. So you've got to think of some other way that you can do that. I'll leave you to have a little think. You can pause here, just a hint, think about pressure. I'm going to go and do it. You might be able to do this at home as well. Okay, so we're doing a can implosion practical. So you just put about a finger, half a finger's worth of water into your can to begin with. Then you're going to heat it up. So you're going to need adult supervision to do this. Going to use some tongs from the kitchen to hold the can. Hold it above the heat and let it heat up. Don't place it directly on the flame, otherwise you'll get a horrible smell of burning of the can. This process takes a couple of minutes. You want to get it so that steam is coming out of the top of your can, and your gas particles inside the can will then be hitting against the sides of the can. Gas particles are moving around randomly, and this will increase the pressure within the can. Okay, let's give this a go. Implosion! So originally we put about a finger's worth of water in the bottom of the can. Water particles can move around each other. They take the shape of the container. So we had liquid water at the bottom. There would be some gas particles in the can as well from what's naturally in there in air. So that's mainly nitrogen. About 78% nitrogen, 21% oxygen, and you've got a bit of CO2 and some other gases as well, including water. Then we heated the can up, and we got more and more water vapour, so more and more water in its gaseous state, and that's moving around in random motion, banging into the sides there, causing the pressure in the can to increase. So we're increasing the pressure in our can. The next step, after we left that for some time, heating up, increasing the pressure, is to flip it into your water container, and this will cause the can to cool down rapidly, and that's what causes that implosion, because that pressure drops. And what's happening is your gas particles are changing state to a liquid, to liquid again, and that causes the pressure to drop and the implosion of the can. Steam engines were very important for the Industrial Revolution. They used fossil fuels which were burnt and released water vapour and heat, which allowed movement to be generated. This movement powered lots and lots of different engines, including steam trains. I want you to do some research yourself into these people here, Thomas Savery, Thomas Newcomen and James Watt. So what is combustion? So that's what we're doing. That's what we're doing in the Industrial Revolution, and burning lots of fossil fuels. It's the burning of a fuel with oxygen, which makes up about a fifth of the air. So oxygen makes up about a fifth, 21% of the air that we breathe. When we burn fossil fuels in this air, in this oxygen, it's an exothermic reaction, so it produces heat, water and carbon dioxide. Coal is an example of a fossil fuel. You also have natural gas and oil. So can you try and complete this word equation to show a reaction of coal with oxygen, so the combustion of coal? So coal plus oxygen, it releases water and carbon dioxide. What I want you to now do is try and complete this symbol equation to show me what happens when you react. See, this is going to be carbon, which represents our coal here. It's solid. You've got oxygen. I want you to try and give me the state of matter for oxygen as well. So S for solid, L for liquid, G for gas, and AQ for aqueous when it's dissolved in water. The little arrow is showing that the reaction's taking place, and then I want you to tell me what is produced. So in this chemical reaction, you've got one carbon atom this side, two oxygen atoms this side, and then one carbon atom this side and two oxygen atoms that side, so it's balanced. And the carbon and the oxygen combine to produce CO2. Do you think that reaction is representative of reality? So as I was saying, do you think that reaction is representative of reality? Because it's magically changed. That's the reality of this. Probably not. Well, it's not, because for one, coal isn't just carbon. It's made up of, there's lots of other chemicals inside coal, and that's where it gets its name as a dirty fuel, because lots of the chemicals it does release are pollutants. It also has water locked up inside it as well, and that will be released when coal is burnt. And you balance this chemical symbol equation. So take a look at it, have a think about how many carbon atoms are going to be in this alkane. So use the general formula to allow you to work out how many carbons that's going to be. I want you to try and balance the whole equation to make sure you've got the same number of carbon, hydrogen and oxygen atoms on both sides, so the left hand side and the right hand side of the equation, and also put in a state symbol for this alkane. So that's your answer to that one. Just some little things to think about. So this is the alkane in question. Now with alkanes, they're saturated, so the carbon atoms are saturated by hydrogen atoms. So with an alkane, there will always be double plus 2 the amount of hydrogen atoms compared to the amount of carbon atoms. So in this case, you've got 4 carbon atoms here. You double it, so that's all of those ones around it, and then plus 2 for the hydrogen atoms on either end of the chain. Carbon also has 6 electrons. It's in group 4 of the periodic table, so in its first shell it has 2 electrons, and its second shell has 4, but it has the capability to hold 8. So this means it can form another 4 single bonds sharing electrons, and that is why the saturation works the way it does with alkanes, because they're looking to fill, these carbon atoms are looking to fill their outer shell of electrons, so they're going to form 4 bonds. So 4 for that one, 1, 2, 3, 4 for that one, and so on. Next off, how to balance the equation. So we start off with 4 carbon atoms on this side, on the left hand side, 10 hydrogen atoms and 2 oxygen, and then on the right hand side, why are you here? On the right hand side we have my cat. Let's take a look at balancing the equation. So on the left hand side at the start you have 4 carbon atoms, 10 hydrogen atoms and 2 oxygen atoms. This isn't the same on the right hand side, so we have to try and get it balanced. So on the right hand side you've got 1 carbon atom, 2 hydrogens and 1 plus 2, so 3 oxygen atoms. So the first thing you can do to start getting this balanced is make there be 4 carbons either side. So for this we have to make there be 4 molecules of CO2 over there, and that balances the carbons out. So the next step we can take is to try and balance out the number of hydrogens, and to do that we add 5 in front of the water there. So we have 5 molecules of water. We can see that also changes the number of oxygen atoms as well. However, the oxygen atoms are still not balanced. So to solve this, what we do is we just put a 13 in front of the oxygen, because that would then allow us to balance it out. It's going to double it. So once we've doubled the oxygen, it's not quite right over there now. What we can do is, but the other things are still balanced, is just double everything, and that will allow us to balance it out in full. So if we double everything else, we end up with 8 carbons either side, 20 hydrogen, so you've got 2 times 10, that gives us our 20 hydrogen, and 26 oxygen. So we put in 13 there, so 13 times 2 gives us our 26. We've doubled this up to 10, so originally it was 5 and now it's 10, and we've doubled this one up from 4 to 8, so originally that would have given us 4 times 2, so 8 oxygens, but now it gives us 8 times 2, so 16. So then we add those together and you end up with 10 plus your 16, 26 oxygens. So that's how we balance the equation in this case. What fuel is this alkane with 4 carbon atoms? It is butane. It's the same stuff that you will find in a camping stove, and I'm now going to use it to make some butane bubbles and some fire. Lucky you, Rob. Some butane bubbles. To do this, you need some washing up liquid, some water, and a container that you can use. Put the washing up liquid into your container, give it a good stir, good mix. With plenty of bubbles, and then you're going to be injecting some butane. So you might have a gas stove at home. You're going to be injecting some butane into those bubbles. Got some butane bubbles here. I'm just going to set fire. Oh! No, it doesn't. And now we're going to set fire to the whole bowl worth of butane bubbles. Stand back a fair distance, move the explosives away, safety is considered, hair out of eyes, and fire. And fire.
She made it wet. It's not firing.